So like I was saying, thiols are known for their unpleasant odor, and for this they use methanol as an additive to natural gas to be able to detect it when there's a gas leak. The hydrogen sulfide anion is a great nucleophile and a weak base, and so it promotes SN2 reaction rather than E2. So if you're going to predict the outcome of the following reactions, we will know that beyond the reasonable doubt, both reactions are going to go SN2, and we proceed with inversion of configuration. Thiols have a pK of about 10.5. Recall that water has a pK of 15.7. So in this kind of reaction, we know definitely that the reaction always favors the weaker acid, and so the reaction favors the product side. Even if we didn't have pKa values, we can always rationalize it, because the negative charge on a bigger atom like the sulfur is going to be more stable. So the reaction will always favor the more stable conjugate base. Now the thiolate can attack the bromine to produce the disulfide. So you can see here, you start with two thiols and you get the disulfide. And notice that this is an oxidation, because you're going from -2 to -1. So this is an oxidation. See, notice how the thiolate attacks the bromine, and then you get this intermediate, which is now attacked by a second unit of the thiolate, and that's how you get the disulfide. So make a note of it. Okay. And disulfides can be reduced by the reverse reaction to the thiols, right, in the presence of zinc dust in acid. Okay, that's a reduction. Again, you can see that the oxidation state goes from -1 to -2. The interconversion between thiols and disulfides can also occur directly via a free radical mechanism. I won't be proposing anything like that this time. The bond dissociation energy of the sulfur bond is quite weak. So it's quite weak, so it's easily broken. And if it is easily broken, we know that we can form two radicals. And of course, that's how the reaction is going to proceed. Now, sulfur analogs of ethers are called sulfides or thiol ethers. So remember, we have, this is a diethyl ether. All you need to do is just replace the ether with sulfide. So this will be diethyl sulfide. Now, when in contrast to when you have an alkoxy group, which in this case is a methoxy group, right? You can have, when you have the thiol, the methyl thiol, in this case, this is going to be called methyl thiol group. So methyl thiol group. So that's how you call the substituent of a sulfide. So when you have a sulfide as a substituent, you call it the methyl thiol group. Okay. Now, sulfides are generally prepared by a nucleophilic attack of the thiolate, just like in the Williamson synthesis. Remember, in the Williamson synthesis, you need to have an alkoxide, and so this will react with an alkyl halide, and that's how you arrive at the ether. This is pretty similar, just like the alkoxide. You have the thiolate, which gets to react with the alkyl halide to yield the sulfide. Okay. And how a thiolate is prepared? Pretty straightforward. To make a thiolate is pretty straightforward. Remember, if you start out with maybe like, if you start with a thiol, all you need to do is make that react with sodium hydroxide, and you get the thiolate. Okay, you get that and water. So this is now your nucleophile, which you can easily prepare. Now reactions, look at the reactions of sulfides. Sulfides undergo a number of reactions which are not very common to ethers. And that's because the sulfur atom is much bigger. So you can actually have the alkylation of a sulfide. So you can have the alkylation of a sulfide, and so the sulfide becomes an alkylating agent. See, so you're able to alkylate the sulfide, right, as shown here, and then this can now react with a nucleophile. So this can act as an alkylating agent. You see, so the alkyl halide can react with the sulfide, and you get the sulfonium cation, right, which will now react with the nucleophile, and so you have this the transfer of the nucleophile from the you have the transfer of the nucleophile of the alkyl group from the alkyl halide to the nucleophile. You see, so that's basically what happens. Now, sulfides can also undergo oxidation. You use an oxidizing agent to go from the sulfide to the sulfoxide and then to the sulfone. Make sure you know what the sulfoxide is and the sulfone. Remember, we had DMSO, which is a good solvent for SN2 reactions with dimethyl sulfoxide. Or you can use sodium metaperoxide, which can form the sulfoxide. So this is something you want to make a note of. How do you go from the sulfide to the sulfoxide? Use sodium periodate. Now, sulfides can also be oxidized to the sulfone, but you got to use a very strong oxidizing agent like hydrogen peroxide. So if you use 2 equivalents of hydrogen peroxide, you can take the sulfide through the sulfone. You see, note the sulfide to the sulfone. So make a note of that. If you want to stop at the sulfoxide, you have to use sodium periodate. But if you want to go all the way to the sulfone, then you have to use hydrogen sulfide and hydrogen peroxide. I'm sorry, you got to use hydrogen peroxide if you want to go all the way to the sulfone. Now, sulfoxides and sulfones have very, very little double bond character. They have very, very little double bond character. You see, and that's because of an inequality of the sides of the sulfur and the oxygen. You know, so very, very little double bond character as a result. Because the 3p orbital of the sulfur and the 2p orbital of the oxygen are not of the same size, and so they will not overlap nicely. Okay, and that's why you can see that this will be the most significant resonance form, because overlap is almost impossible. So remember, over here you have the 3p orbital, and here you have the 2p. Now, how can a 3p overlap effectively with the 2p? The 2p is smaller, right? So it won't be able to overlap well. Now, because sulfides are readily oxidized, they make good reducing agents. See, and that's why we use DMS to be able to convert this molozonide to the corresponding carbonyl compounds and DMSO. Okay, so if you think about it, if this reaction were to go, you know that you can have this attack like this. Of course, this is going to break like that. This is going to break like that. And so what's going to happen is that this is going to break like that. Or it's going to break like that, and they're going to have the breaking like that. See? So eventually you're going to have this is what you're going to have. See, which eventually has a resonance form like that. So basically that's what happens. See? Now, we're going to predict any products or necessary reagents here. You see, if you want to form the sulfoxide, you see, first of all, you have to make the hydrogen sulfide nucleophile react with an electrophile, and you get this compound here, and then in the presence of sodium periodate, you can now convert the sulfide to the sulfoxide. Now, epoxides can be used to install functional groups on adjacent carbons. As you can see here, if you have a double bond, you can first convert it into the epoxide and then use a nucleophile to attack. And notice again that the nucleophile comes from the less hindered side. The nucleophile comes from the less hindered side. And if you want to think about how this reaction happened, you don't have to think too far, because you know that this will first of all be converted to the epoxide. Okay, it's going to be converted to the epoxide, and of course, in the presence of NaCN, you're going to have water. Okay, you're going to have the formation of that. Now, by reacting an epoxide with a Grignard reagent, you can actually modify the carbon skeleton. You see, you can add a given number of carbons to the carbon skeleton. So you might think of an epoxide as a good starting material to which you can add carbons. Now, an epoxide can be used to install a 2-carbon chain between an R group and an OH group. Okay, a 2-carbon chain between an R group and OH. So you see, you have an R group, you can install it like that. The recall that the carbonyl can be used to install a carbon chain between an R group and an OH group. So if you have something like this, notice that if you had a Grignard, like that, you want to make this react. So you can have something like that. So notice that you have installed 1 carbon in between the R group and the OH group. Now, if you want to install 2 carbons, then you have to use an epoxide. That's what is happening here. You can see that in between the R group, this is the R group, and the OH group, you need 2 carbons. So you have 1 carbon and you have 2 carbons. So to do that, you have to first convert this to a Grignard in 1, and then you add the epoxide in 2, and then you hydrolyze. And that's how you arrive at that. Okay, and this is pretty straightforward. The very first thing you want to do is, of course, is make your Grignard. See, so you make your Grignard. That's the very first thing. See, you make your Grignard, and to make your Grignard, of course, you know that to make your Grignard, pretty straightforward. You make a Grignard in presence of magnesium and ether. So you get your that, and then you make this react to that. And remember, because this is your nucleophile, the reaction is going to attack through the less hindered carbon. See, it's going to attack, so this is going to open up like that. And of course, you're going to get your of course, in presence of water, you're now going to get your product. Notice that we have added 2 carbons in between the R group and the OH group. We have added